Electric potential difference is one of the most misunderstood things in physics. A lot of people struggle with the idea, and it's kind of surprising because it's very, very common when we do electricity. Can the phone please go away? Thank you. So what we said in the story yesterday was that once upon a time, there were 3 charges that went out for a walk. They each had a certain amount of joules in their hands, 3 joules per little charge. They went for a walk around the neighborhood, and as they got to the big bad light bulb, they went, ah! And they gave away all their charges to the light bulb, right? And they went home chargeless. Not chargeless, I say charge, energyless. Energyless. They gave away all their energy, and they went home energyless. But one of the morals of the story was that charges don't get destroyed by light bulbs, but they do lose their energy. Okay? Then the next story we told was about the same 3 charges going out for another walk the next day. And the next day they went for a walk, each with a few units of energy. And as they went around on their walk, they encountered a big bad light bulb. And they said, oh no, we'll give you our energy. And but they said, we have to be able to get home again. We can't give you all of our energy because there are 2 more light bulbs. And so they gave energy to the first light bulb, but not all of their energy. And then the same thing happened to the second light bulb. They said, we'll give you our energy, but we can't give you all of our energy because there's 1 more light bulb. We won't be able to get home if we give you all of our energy. And of course, they get to the last light bulb, and they give up the last of their energy, electrical energy. And as they travel home again without energy, again, the electrons are not destroyed. The charges aren't destroyed, but they do give up their energy. And people make these analogies like, oh, this is like a shopping trip. You go out shopping, and you know you're going to spend all your money, and you always come home broke. It's just like shopping. I hate that analogy. Some people say, oh, this is really like a waterfall, where this is a pump, and the water gets pumped up to a certain gravitational potential energy, and it falls down the waterfall and gives up its gravitational potential energy in the form of kinetic energy, and at the bottom, it returns back to the pump to repeat the cycle. That's a slightly better analogy. But the best thing to understand is what's really happening. These are electrons. They're not waterfalls. They're not shoppers. They're electrons. And these electrons, these charges, are going around a pathway. They're encountering something that's going to resist their motion. And as it resists their motion, it requires them to give up energy. And as they give up energy, they become de-energized, but the energy doesn't get destroyed. It gets passed off to the thing that resisted the motion, just like when we were talking about kinematics and dynamics and energy and mechanical systems. And they travel back to the battery again. And it's an electrochemical reaction, oftentimes, if we're talking about a battery, that's driving this motion and giving the electrical energy to these charges. And the charges don't get consumed. That's really important to remember. Now, when it comes to a system like this one, now this is what we might call a simple parallel circuit. There's a parallel junction here in the middle. If we go back to the fairy tale, there's these little charges. They go out for a walk one day, and of course, charges follow the path of least resistance oftentimes, but they will follow any path that's a complete path. And these charges may follow each of the paths. So one goes one way, one goes another way, one goes the other way. And upon reaching this light bulb, this light bulb, this light bulb, since there's no other light bulbs in their pathway, they give up all of their energy. Okay. What I want to talk about now is not the fact that they gave up all their energy eventually. It's not even the fact that all 3 of them lost their energy. I want to talk about how much energy each charge loses, how much energy is lost per charge. This one here, how much energy was lost per charge? 3 units of energy. That's 3 units, that's it, right? We could say 3 joules per, and if we don't call these charges, let's say that they're bundles of charge, 3 joules per coulomb. Is that doable? Yep. That's not a charge anymore. We're going to say that's representational of a coulomb of charges. We lost 3 joules per coulomb. What about here? If I were to draw a voltmeter here, how many joules per coulomb were lost there? 1. And how many joules per coulomb were lost across here?
1.
And so on. We could do the same thing here. 1 joule per coulomb. That's not to say that there weren't 3 joules lost. Look, there were 3 joules lost, but they were lost by 3 coulombs. We could say that, look, there's 3 joules lost per 3 coulombs. That's the same thing as saying 1 joule lost per 1 coulomb, right? Here, 3 joules lost per 1 coulomb. We could say there's 9 joules lost per 3 coulombs, but that works out to being 3 joules per coulomb. It's the amount of energy that gets lost per coulomb, okay? Same thing over here. If I did a voltmeter connection across this load, this light bulb, a light bulb is a load, it's a user of electrical energy, how many joules per bundle of electrons were lost there? 3. 3 joules per coulomb. I want you to notice that's one light bulb that it encountered. That's one light bulb that it encountered. 2 identical light bulbs, I suppose. And this one lost 3 joules per coulomb. This one lost 3 joules per coulomb. Now thinking about this, for every electron that goes through here, 3 joules per coulomb are lost. For every electron that goes through here, 3 joules per coulomb are lost. Which one gets more energy per electron? Or is that a trick question?
It's the same.
Same, yeah. What about this one here? If I compare this guy to this guy, which one gets more joules per coulomb of electrons? The first one or the second one? The one on the left? Yeah, the first one does. Okay? That's what voltage is all about. How many joules of energy get delivered per coulomb of electrons? And that's not terribly well understood. Okay? Not terribly well understood by people that are first learning. But I want to make sure that maybe through a fairy tale method, maybe by the idea of water pumps, whatever analogy you like, we get the idea. But at the end of the day, it's more important to understand what's really going on. That's what I care about. And that's what you should care about too. So we've got our formula. Voltage is the change in energy in joules per coulomb of charge. And we say that the units, 1 volt, is the same as saying 1 joule per coulomb, or 1 joule per 1 coulomb. So joules per coulomb and volts are equivalent units. And of course, we could break down joules and we could say, oh, well, we all know that joules are kilogram meter squared per second squared. But do we really care about how many kilograms of electrons we have? Not really. So let's just leave it as joules. Okay. All right. Some people like to say it's voltage not equal to change in energy, but equal to the work it takes to move an electron from one side of a load to another. I'm not a big fan of that, but you may see that from time to time, and sometimes the textbook talks in those terms. I'm not a lover of that. We know that the amount of work done and the change in energy is an equivalent statement. Okay? All right, so last day, we can call this equation 1. Last day, what we said was we had this other equation. I'm going to call it equation 2. We said that current was defined as being the amount of charge that goes past a point in a circuit per unit of time that passes. Now, I'd like to do a little bit of rearranging for each of these equations so that for this one here, I'm going to rearrange it so that energy is all by itself. I'm going to say delta E is equal to V times Q, voltage times charge that's moving across that voltage. And for this one here, I'd like to rearrange it so that it's in the form Q is equal to I, or current, times the amount of time that goes by, delta T. And so I'd like to take this guy here, and I'd like to do a little bit of substitution. I'd like to sub the second equation into the first equation. Sub in. So I'm going to get a formula. Delta E is equal to V, and somebody said VIT. Yeah. EVIT. The amount of energy that's being used by a circuit could be measured. Can you see that each of these values are measurable values if you have a multimeter? You can measure voltage across a load. You can use an ammeter to measure the current flowing in one side and outside going through a load. And if you like, you can use a stopwatch to calculate or to measure delta T. Which really means we can sit down and calculate how much energy is being used by a circuit or a load. Okay, this is very calculatable, and the units are going to end up being joules. What's that? Oh, sorry, never mind. So we could calculate, for example, the energy required to keep a light bulb glowing for a certain amount of time if we measure the current flowing through the light bulb and the voltage across that light bulb. But the energy required or used by a circuit or a junction within a circuit.